them up. So, Organic Chemistry 2330, Introduction to Organic Chemistry. We're going to continue on with Chapter 11, Spectroscopy. Specifically, we're going to talk about, our goal today is proton NMR. And so I'm going to give you a little bit of background on what NMR is that'll also satisfy how it works for carbon-13, but we're going to look for different things in proton NMR versus carbon-13 NMR. And so I wanted to kind of split those out because that way we have 4 things to learn in proton NMR and only 2 things to learn in carbon NMR, but they both use the same kind of radio frequency kind of system. So we're going to start with that. So administration wise, I cannot find any better amine questions. So what I'm going to do is I'm going to open up the homework, and even though there's only 3 questions, I'm going to make them worth 10 points. And so that will be done here toward the end of class. Let's see, I might even be able to do it right now, actually. So there really aren't that many questions I can find with amines. So that's what we're going to do. And so those are going to be updated to be released and assigned now, so that you guys can go ahead and complete that and do the self-check after that as well. Now until, again, they'll be due Friday at noon. And they will be graded, and the self-test will not be graded. So, all right. So yeah, all of the questions and stuff will be on the amine. Have you decided how many questions are on exam 3? Right now, I think I have, let's see, 22. I'm going to add 3 more. So there'll be 25 questions. No, there'll be 2 more. There'll be 24 questions on exam number 3. So, and it's going to boil down to, a couple of the questions are going to be kind of at NMR and IR together to kind of try to figure out a compound. I'm only going to do that a couple times, because we're going to do that as part of our exercise on Thursday. And so the exercise will actually be the hard work while we'll do it together. And then the one on the exam will be a little bit easier. So, okay. So I think that's all the questions currently in Zoom. We'll be allowed spectroscopy. For this exam, the answer is no. I'm going to ask simple enough questions that it should be, like, which band does this functional group show up in, that kind of thing. So if we look at IR, we have those 4 bands. We know where the different bonds will be in those different bands. NMR, we're going to look at different types of hydrogens and shift of those hydrogens, and those are going to show up in different regions. And so it will be a clear enough and only a 1-piece question for spectroscopy, so you will not need the reference. All you'll need is kind of a working understanding of the general idea of how it works. And so that's what we'll be doing for spectroscopy. If you were in my spectroscopy class, which I also teach, we actually use you can use the book. The book has all the reference materials in there, and then the questions get really hard. But we're not going to do that. All I want you to know is the different regions where things show up, and the certain things about proton and carbon NMR, like shift. Those are the things we're going to be doing more. Okay, so now that we're already recording, I'm going to go ahead and share my screen, and we're going to start with part 2 of chapter 11 here. There we go. So, and then let me move the people over here so that I can gather. All right, so got people over here, got my participants list over here. have my Zoom chat, so I'll be reading that as we go. But let's go ahead and continue on with our spectroscopy, specifically goal number 2, proton NMR spectroscopy. IR is all about the actual bond between two atoms and its vibration, and that it absorbs that energy, and you can see that, right? So if IR is all about the bond energy, proton is all about looking at different kinds of hydrogens you have on a compound. So IR is all about individual bonds, and so you can find functional groups. NMR is about where the hydrogens are along your organic molecule. And so that's why they are different and they're complementary. IR tells you a lot about functional groups, but not necessarily about how things are connected. Proton NMR is going to tell you about where the hydrogens are, which gives you an idea of where they're connected. And then the final piece of the puzzle is carbon-13 NMR, which actually tells you how the carbons are connected together. And so we'll be able to, between all three techniques, you'll get functional group, where the hydrogens are, and then where the carbons are, and you'll end up with a full understanding of the organic molecule. And so we usually use all three of them together when we identify new compounds. All right, so let's talk about NMR spectroscopy, and it's a molecular spectroscopy, but what we're looking for is, instead of the vibration or the bond between two atoms like we had in IR, we're actually looking at the nucleus of each type of atom, okay? So one of the things that is important to this is that the nucleus must have an odd number of protons and or neutrons. This total sum has to be an odd number. And what we'll see that is that we can do spectroscopy on a variety of different substrates. The two most common are hydrogen, which has the atomic mass of 1, and carbon-13, which has the atomic mass of 13. That's what those numbers mean. That's the type of isotope we're using, okay? There are other isotopes. The most common isotope of carbon is actually carbon-12, but we don't see it by NMR spectroscopy because there's something about the nucleus that it doesn't have. And what it doesn't have is an odd number of protons and neutrons, okay? So what we want to look at here is, in the origins of NMR, is that when you have your protons and neutrons in your nucleus, they have what we call spin. And whenever you have spin, you have like a little magnet, and you have an up side, a north side, and a south side of a magnet. And so what happens is, in the nucleus of the atom, these are randomly oriented. They're pointing in, any of the 360 degrees in any direction possible. And so we can't really, because they're all in a different orientation, they kind of all cancel each other out, okay? So we don't really see them or feel them or hear them, okay? So, but in the case of NMR, what we do is we take a strong magnetic field, and when we have that strong magnetic field created, what happens is all of the magnetic poles on each individual proton and each individual neutron will line up with that field, either up or down with that field, okay? So if we look at this diagram here, we see that before we apply our magnetic field, we just have them randomly oriented in any old direction. And then once we put a huge magnetic field in that, they all line up, either with the magnetic field or against the magnetic field, but they all line up in that field. That's the first step in NMR, okay? So now that we have these things all aligned there, and we have an odd number. So because we have an odd number, if each of these downs are a half minus and each of these ups are a half plus, the net result of these things in the magnetic field is a plus 1/2. If we have that plus 1/2, that means we can see it by some other electromagnetic spectrum technique. And we're actually going to use radio frequency to be able to do this, okay? So we have these randomly, stop mirroring, start mirroring. So we have these randomly ordered things we put in a huge magnetic field, and then they align, okay? So that gets it where we're just starting the experiment. We haven't seen that we know there's a difference in the number of protons or neutrons. We know that there's a spin alignment there's half of them are aligned with and half of them are aligned against right here, but we don't really see it. Okay, and the reason we don't see it is because we don't have a way to sense it. And so what we do is we hit it with a radio frequency, like a high frequency radio wave. And what happens when that high frequency radio wave hits it is it inverts the spin of some of these protons and neutrons. When it does that, this is what we call its high energy state. Okay, so we've taken it from where it was low energy to its high energy state. And now we have done what we call pulsing, okay? So we've changed the order. Now, when they relax, when they go back to the other sense, they're gonna release energy again. And when we release that energy, that's the energy we're sensing, okay? So we have neutrons and protons, neutrons and protons in the nucleus of the atom. They're randomly associated until we put them in a magnetic field. Then we hit it with radio frequency, and then we listen for a radio frequency response. And the time it takes for that to relax tells us something about the electronic configuration around that particular species. Okay, that's the whole thing. That's what's happening in there. So this is just kind of what's happening and why it's happening, and why every time you see an NMR, it's going to be in an odd numbered isotope. This is the fundamentals, but we'll get to the basics here in a little bit. Okay, so what we have, wait, let me get the machine. Nope, that one. I want to show you what the machine looks like. Okay, so in the machine here, we have this really, really powerful electromagnet. Most of the time we actually use superconducting magnets. This actual technique is also used in medicine. It's called the MRI, or magnetic resonance spectroscopy. And so imaging. And so they actually are doing the exact same thing in the human body, except they're mapping it out spatially. Here in our technique, all we're going to do is do one chemical at a time, and we get a very simplified image of what happens. But the idea here is that you have this huge, oops, wrong. We have this huge magnetic field going on in this direction here, and then we pulse a radio frequency in one side, and then we wait, and then we listen for the radio frequency that comes out, okay? So imagine that you're going ping, and then you wait for it to go ping, 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 back. And so each of those different pings is a different type of hydrogen that's relaxing at a different time in place because of the electronic configuration around that actual hydrogen. Okay, so that's what the experiment looks like. And again, that general idea will not be on the test. What we're going to do is we're going to talk about something else. Okay. So the first thing I want to talk about is, how do we know what zero is? Okay, we're gonna have a spectrum that's going to have two axes, and we need to know where zero is. So what they figured out is that this compound right here, which is called tetramethylsilane, if you'll see here, the center here has a silicon atom, and that we have these methyl groups here on all sides. So the good thing about this is we have a very clean molecule. All of those methyl groups are identical, okay? Because they're all bonded to the same silicon. That silicon spaces them out such that these protons don't see these protons or hydrogens. The hydrogens are what we call protons in proton NMR. And the carbons don't see each other either because of the silicons here in the middle, and it's nice and big. So what that means is we have a very pure carbon signal, and we have a very pure hydrogen signal. And because of where these showed up, turns out that we are calling these hydrogens our zero shift, meaning that's where zero is on all of our NMRs in proton NMR. Zero is these methyl hydrogens here. In addition, in our carbon NMR, because these carbons are isolated and only have 3 hydrogens on it in the silicon bond, we also call that zero in carbon NMR. So We use the same molecule to say where 0 is from the beginning and end, and everything that shifts from that position is what we call shifting up field, okay? And what that means is that these atoms have a certain electronic configuration, and by having more or less electrons around them, they're going to shift further and further to higher and higher numbers, okay? So that's a lot of information. All right, now let's condense it down into the most important things, okay? So the most important thing is what I like to call spin, okay? So it's an acronym that tells you the 4 things you look for in every proton NMR. In carbon NMR, we're only gonna look at 2 things, which is number of signals and position of signals. But right now, in proton NMR, we're gonna look at 4 things. We're gonna look at the number of signals we have. That tells us how many different types of hydrogens we have, okay? We're gonna look at the intensity of the signal by taking the area under the curve, or we can actually say there's exactly 3 hydrogens for 2 hydrogens for 1 hydrogen. We can tell you how many hydrogens you have in that thing. Next is the position, how far it's shifted away from that silicon compound, TMS. How far it's shifted away from there tells us something about what functional group that hydrogen has to be next to. And then the last thing we have is what we call spin-spin splitting, meaning that hydrogens that are the same don't split each other, but hydrogens that are different change the signal. And we're going to talk about that in detail as well. Okay, so this, if you look at the acronym backwards, it is spin. So these are the 4 things we're looking for. Spin-spin coupling, position, intensity, and number, okay? So please write that down and know what each of those things are, because we're gonna look at each individual spectrum for all of these things, okay? So now, to remember what we're talking about with spin right here, this is just the generalized NMR, and I want to show you around this NMR spectrum so that we can look for the 4 different things in our system, okay? So one thing I want you to notice is most of the time we have 0. Notice that the 0 here on the x-axis here, there's usually a little bit of this TMS, tetramethylsilane, in there to show you where 0 is, okay? And that's so that, number 1, you're sure that you are having your shifts set up correctly, and because almost always we put it a little bit in the solvent just to make sure that we can calibrate to that particular number. So we start at 0 and then we go up, okay? So this number on a proton NMR can go from anywhere up to approximately 15 for some things, but most of the time we're gonna see this between 0 and 8. Now the number, the term, the value, the unit here is what we call ppm, okay? So that's parts per million is what it's really named, but what you wanna think about it is shift. It's moving over 1 ppm here, it's moved over 2 ppms, 3 ppms, 6 ppms, 7 ppms, 8. That is our shift of our spin, okay? So our spin splitting is the fact that our peaks will have more than 1 peak if there's more than 1 type of hydrogen next to it. We're going to talk about that separately. So because there's 3 protons here and 2 protons here next to a bromine, these are not the same. And therefore we are going to end up with 2 different peaks, an A peak and a B peak, okay? So that's the M, number of peaks, okay? And that's because we have 2 different kinds of hydrogen, okay? The next thing we have is I, intensity, okay? If we took if we mathematically took the total area under these curves, or the value of this peak would equal to 2, and the value of this peak would be equal to 3, okay? Why, okay? We have 2 hydrogens attached to this carbon. We have 3 hydrogens attached to that carbon. So we actually know exactly how many hydrogens we are because of this intensity. So this is number of peaks. And the intensity tells us number of hydrogens compared to the other hydrogens. Okay. Okay. P, position. Position is all about how far it shifted over. Notice this carbon right here, these hydrogens right here shifted over about 1.5 ppm compared to TMS. And this is almost at 3.5 ppm versus TMS. So that's our P, is position, okay? And then our S is this splitting pattern here. And we're going to talk about that separately. Okay, so questions about the 4 things we look for and a generalized look at what an NMR spectrum should look like. Okay, hack, 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 type, 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 type. All right. So let's look at what we mean by the number of peaks we're going to have. Okay, the number of peaks we have is all based on the number of equivalent hydrogens. Okay, equivalent hydrogen really means the number of the hydrogens that are in the same environment. Okay, meaning that if we picked a hydrogen and looked at it in a different part of the molecule, is it going to see a different environment? Like, is 2 bonds over attached the same way, is 3 bonds over attached the same way? So that's what we're looking for. So let's do an example of this where we're going to look at this compound right here, this 2-methylpropane. Okay. Now remember that this is just our stick drawing. It's just showing us where the carbons are. So if we have to, go ahead and write in the hydrogens you have here. So you have 3 hydrogens there. You have 1 hydrogen here because there's only 3 carbons to that. And then you have 3 hydrogens here and 3 hydrogens here. Okay. Okay. Now, let's take a look at this again as figuring out if they are different or not. Okay. So let's look at these hydrogens here. I'm going to just put this methyl group here in blue. And we're going to say those hydrogens, they have, there's a hydrogen bonded to a carbon with 1 hydrogen on it and bonded to 2 other carbons. Okay. So this hydrogen here is different than this hydrogen because this hydrogen is bonded to a carbon with 3 other carbons to it. This hydrogen is bonded to a carbon with 3 other hydrogens to it. Sorry, 2 other hydrogens. So do we see that these hydrogens are different than these hydrogens? Okay. So one has 3 hydrogens on a carbon, one has 1 hydrogen on a carbon, therefore they are different, right? Okay, so we know that these are not equivalent to these, okay? But let's look at the next one. Let's look at this green methyl group here, right here. Okay, so if we look at that green methyl group, that's this carbon here with a hydrogen here and a hydrogen here and a hydrogen here. And so this carbon has a carbon hooked to it with 1 hydrogen on it, hooked to 2 other carbons. So wait a minute, that's exactly like the ones up here in red, in blue right here. These right here are all equivalent and they're these, but these have exactly the same environment. They have exactly the same connection as this. We have our carbon in the middle with 1 hydrogen on it, and then this is a methyl group. This is a methyl group. That means that the green carbon there is equivalent or has the same electronic structure as the blue methyl group there. Okay, so we can expand that again and say, okay, let's look at this yellow carbon over here. Okay, it's going to have a carbon with 3 hydrogens on it attached to a carbon with 1 hydrogen on it attached to 2 other carbons. So it is also equivalent. Okay, so when we're talking about equivalent hydrogens, it's the connections. How many connections are exactly the same? The hydrogens here are connected exactly the same as the hydrogens here, as we move out along the methyl chain. Okay, so that's what we mean by equivalent hydrogens. Let's do that one more time with the next species here. This is the methylbutane. Okay, so this was really symmetrical. So the idea of being equivalent and non-equivalent might be oversimplified. So let's try it again. And let's look at a couple different things here, okay? So we have this methyl group, and this methyl group here, okay? Now, I think that they are not all the same, okay? This is why, okay? If we drew this line here, so this is a methyl group hooked to a carbon with a methyl group on it, and then a methylene over here, a CH2 group. Okay, this one is a methyl group that's hooked to a carbon, that's hooked to another CH3 and a CH2. But this one over here, this last one, is a CH3 only hooked to a single carbon with 2 hydrogens on it. Okay, which means that this methyl group number 1 and methyl group number 2 actually are equivalent. They have the same connections, right? 3 hydrogens on this carbon bonded to a carbon with 1 hydrogen, bonded to a carbon with 3 hydrogens, bonded to a carbon with 2 hydrogens over here. This number 2 is a carbon with 3 hydrogens, bonded to a carbon with 1 hydrogen, bonded to a methyl group, bonded to the methylene. So that means all the hydrogens on carbon number 1 are equivalent to all the hydrogens on carbon number 2. Okay. So that means 1 and 2 is going to give us 1 peak. Okay. So now let's identify the one over here. Is there any other methyl group exactly like that? No, because we only have the methyl group that's attached to 1 carbon with 2 hydrogens on it. We have no other methyl group like that. So that means this is going to give us a third type, or our carbon number 3 here is different. So carbon number 3 is not equal to 1 or 2. So that's going to give us a different set of hydrogens to look for. Correct. The question is, are the carbons on number 4 different? Wait, are the hydrogens on carbon 4 not the same as the carbon on 1 and 2? Okay, I haven't identified number 4 yet, but the carbon number 3, they're definitely different. Do we see that? That they're different? Oh, okay, going back, the question is, are the hydrogens on carbon 4 not the same as the carbon on 1 and 2 in the 2-methylbutane? Okay, so in 2-methylbutane, I'm going to call this carbon 1, this carbon 2, this carbon 3, and this carbon 4 in the middle here. Okay, so carbons 1, 2, and 3 are all identical, which means their hydrogens are all the same. So 1 is equal to 2, which is equal to 3. Okay, the fact that this hydrogen on carbon number 4, the fact that there's only 1 hydrogen on that carbon and it's bonded to things, that means it's different. Okay, so 1 is equal to 2 is equal to 3. However, it's not equal to 4. Okay, so what that means is we'd have 1 peak for all of these and 1 peak for this. Okay, so we have 2 different types of hydrogens on this compound.
So I see that on the methylpropane. I understand what you're saying, but on the 2-methylbutane, the next one, for the far left carbon and then the second, so carbon 1 and carbon 2 are the same on methylbutane, but is carbon 4 not the same as 1 and 2?
Let me label this one 4 and this one 5. How about that? Okay, which one are you talking about?
Sorry, I was referring, I guess, to 3, then the one in the red.
Okay, so why is 3 not the same as 1 and 2? That's what you're asking.
Yes.
Okay, so what we have to do is look at the connections here. So let's say we have a hydrogen here on this and a hydrogen here on here. So if we have a hydrogen-carbon bond, a carbon-carbon bond, and this, so this carbon has 3 carbons on it, right? 1, 2, 3. And so if we look at the connection, we have this hydrogen is bonded to this carbon through carbon number 1. This hydrogen is bonded to the same number 4 carbon through carbon number 2. Okay, so if we look at this, you think about equivalency as having the same connections going through approximately 3 bonds. 3 peaks in propane. Let me answer that question next, okay? So do you see that the carbon 2 is the same as carbon 1? Is that true?
Is it because they're both connected by carbon 4?
They're both connected by carbon 4, and carbon 4 is, so it has the same number of hydrogens and they have the same connections, right? So 1 and 2 are identical. But that means carbon 4 is different than the carbon 1 and 2, just like in the 2-methylpropane over here, because it only has a single hydrogen on it. So that means carbon number 4 is also different. Do we see that? Okay, so carbon 1 and 2 each have 3 hydrogens, so, and they have the same connections. Carbon 4 only has 1 hydrogen, and there's no other carbon with just 1 hydrogen on it, so that hydrogen's different. This right here, carbon number 5, has 2 hydrogens on it. There is no other carbon in the system that has 2 hydrogens on it, so those need to be different, okay? And therefore 3, because it doesn't have the same connection, it goes through a carbon with just 1 carbon bonded to it, and these both go through carbons with 2 things bonded to it, that 3 is not equal to 1 and 2. Does that equivalency make sense yet? Okay, so now let's go to the question on, would there be 3 peaks in propane? Okay, so I'm going to draw propane for you. Oops, I drew butane. Let me draw propane. All right, propane is going to be this, CH3, CH3, and then we have 2 hydrogens here. Okay, so let's look at the one in the middle here. Obviously, there's 2 hydrogens on that carbon, and there's 3 hydrogens on the other carbons. So I'm going to say that the middle one is definitely different. That's definitely going to give you a single peak. Okay, now let's look at the other 2. Okay, let's look at this first one here and I'm gonna put it in red first. We have this carbon here. It's hooked to a carbon with a CH2, and then it's hooked to a carbon with a CH3. Okay, so if we're looking at it in that direction there. All right, let's go to the other one. This carbon has a CH3. It's hooked to a CH2, and then it's hooked to a CH3. Okay, so if we looked at the connection between these hydrogens going in this direction and these hydrogens going in this direction, they have the same number of connections to the same types of carbons, meaning that this methyl group and this methyl group are actually equivalent, which means in propane, we actually only have 2 peaks. Okay, are we starting to see what equivalency is now? Okay, now let's complicate things ever so slightly and look at our last compound here. Okay, and I'm going to do it in, let me erase this down here, get it out of our way. Okay, so what we're looking for is things that have the same number of connections. So we're looking for similarities, right? So the peaks are determined by the different types of hydrogens. Yes, the peaks are determined by the different types of hydrogens. All we're doing right now is figuring out which hydrogens are the same and which hydrogens are different. If they're the same, they only create a single peak. If they're different, they'll create two different peaks. And we'll know which were which by how much they're shifted, okay? So if we look at this, we have to think about, oh, we have symmetry here, right? If we drew a line down the middle of it, we have symmetry, okay? Which means that turns out that this methyl group is going to be equivalent to that methyl group. Because if you look at the connections, 1, 2, 3 is the same as the 1, 2, 3 in that direction. So, and it would be the same if you went around the other way. So that means those two methyl groups are now equivalent structures because they are on, they have the same number of connections going in the same directions, okay? So, is there anything the same as this peak on this structure here? Okay, so this hydrogen, right, that would be hooked to here is on a carbon that's hooked to carbons with 3 other carbons on them. This carbon only has 2 other carbons on it, so that means it's not equivalent to these hydrogens. This one's in between 2 methyl groups. This one is not. This one has a hydrogen here and a hydrogen here, so it's not equivalent to either of those, okay? So that means that hydrogen, that green hydrogen, is different. Okay, so since that green one is now different than these other 2, let's look at the other 2. All right, so let's look at the last remaining 3 we have. I'm sorry, the last, 3 hydrogens we have. This hydrogen doesn't look like that hydrogen because it's next to a methyl group. This hydrogen looks like that because it is next to a methyl group. So that means that's a different type of hydrogen, okay? And that makes this last one its own type of hydrogen because there's nothing else like it in the thing. So do we see that we have different hydrogens because of the connections made? So in this compound here, we have 1, 2, 3, 4 different types of hydrogens, which means this is going to give rise to 4 different peaks in our proton NMR. Okay. Am I at the bottom of the thing here? Yeah, okay. So I think I answered all the questions in the chat. Okay, so now all we did here was we were looking for equivalent hydrogens. Equivalent hydrogen equals number of different signals, okay? So now let's talk about the intensity, okay? If your hydrogens are the same, then when we do the intensity, we should get that exact number of hydrogens. So let's look at intensity as a function of how many different types of hydrogens we have that are the same, okay? So in the case of this compound here, propanone, or commonly known as acetone, right here, we have a methyl group and a methyl group, okay? Now, if we do the same thing we did last in the previous slide and look at for equivalent hydrogens, we'll see that these hydrogens are equivalent to those because they're both hooked to a carbonyl. They both have 3 hydrogens on it. So they are equivalent, okay? Now, there are 3 on this side and 3 on this side. When we look for the intensity on our NMR, we're going to get a number that is 6 because we have a total of 6 equivalent hydrogens, okay? So let's look at this one, do that same analysis. We have a CH2 that's hooked to a CH2 and it's hooked to a chlorine. We have a CH2 that's hooked to a CH2 and hooked to a chlorine, meaning that those hydrogens are equivalent hydrogens, right? Okay, so we have all of those are equivalent hydrogens. We have 2 here plus 2 here, meaning our intensity is going to give us 4 hydrogens. Okay, all right, throw a wrench into things a little bit here. Cyclopentane, okay? If I look at these 2 hydrogens here, and I go this direction or this direction, these two hydrogens are going to be equal to these two hydrogens because it keeps going around the ring. We don't have an end. So these are all equivalent. So if you look either direction from any of these CH2 groups, they're going to only see other CH2 groups. So by equivalency, they're all equivalent. Okay, that being said, now that we think they're all equivalent, what would the intensity be? Remember, there's 2 hydrogens on each of those CH2s. So we're going to have an intensity of 10. Yes, that's right. Okay, so number of peaks by different types of hydrogens. Equivalent hydrogens give us our intensity, and it's the actual hydrogens. So that being said, let's look at this one right here. I think all those methyl groups are equivalent because they're all hooked to a double bond. So how many equivalent hydrogens would we see in our intensity? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I agree, 12. This is going to give us 12 because there's 3, 6, 9, 12 hydrogens there. Okay, so our first thing is number, which is by different kinds of hydrogens. Our second thing is intensity, the number of hydrogens that are of that type, okay? So now we need to go to the idea of, let me pull this down here. Signals, okay? Number of signals we get is based on equivalent hydrogens. So we can compare the molecule with 2 or more equivalent hydrogens to different signals. Okay, so let's look at this one real quickly. And I'm going to draw this one right here. I'm going to redraw this one just to draw attention to a couple things. Chlorine, hydrogen, chlorine, carbon, hydrogen, hydrogen, hydrogen. Okay, so the first thing we want to look at is, okay, these 3 hydrogens are equivalent because they have the same connection to this carbon over here. This hydrogen is a separate signal because it's bonded to a carbon with 2 chlorines. It's different than the one over here. So now we have 2 different kinds of hydrogens, right? So that means we're going to have 2 signals in our NMR because we have 2 different types of hydrogens. Okay. When we look at the intensity of these 2 signals, the first signal is going to have 3 intensity, and the other one's going to have a single intensity. All right. Now, let's look at something with a ring that has something that breaks symmetry. Okay. Unlike the cyclopentane on the previous slide, we actually have a carbonyl here, a C double bond O, which makes these hydrogens now different because they're close to this carbonyl compound. These are a whole CH2 away, so we're going to end up with 1 signal for these and 1 signal for those. And because there's 2 and 2 here, that's going to give us 4 protons. 2 and 2 is going to give us 4 protons. Okay. Now, this one's even going to be more interesting here, this next one in blue. Okay, this hydrogen is not like this hydrogen because it's bonded to a carbon with a chlorine. This is bonded to a carbon with another carbon bonded to it. So that means that those hydrogens are not the same. Therefore, we're going to have different signals. Okay, so this hydrogen's different than this hydrogen, and both of these are attached to a double bonded carbon, and that makes these hydrogens different. So we get 3 different signals, and if we looked at the intensity of these signals, we would have an intensity of 1 for A, 1 for B, and 3 for C. Okay, so got to add one more thing to it. When we look at this cyclohexene, These are going to be somewhere else because they're bonded to the double bond. These are next to the double bond, and these are far away from the double bond. So we have 3 signals. And again, we're going to have 4 hydrogens, 4 hydrogens, and 2 hydrogens. Okay, are we starting to see that pattern? Are we starting to see what connections make equivalent hydrogens and how many hydrogens we're actually seeing on the compounds? Okay, great. All right, so let's move on to the next thing. So we have number of signals, which is our N. We have intensity of signals, which is our I. So now we're going to look at position, which is our P. Okay, position is all about how far away from that TMS is. So we, by definition, our TMS right here is always 0. And so we're looking at things that are shifted positive of 0, okay? So think about that. You have a methyl group on that TMS. So things that are kind of like methyl groups are going to be close to it, but if they're bonded to a carbon instead of a silicon, that makes them shift to approximately 1. So a methyl group that is not bonded to a silicon is going to be around 0.8 to 1 ppm. That's the shift, okay? And the unit is ppm, parts per million. Okay. So if you had a CH2 that's bonded to 2 carbons, that shifts a little higher, just above 1. And then if you had a CH bonded to 3 other carbons, it shifts it even a little higher. So 3 hydrogens are going to be lowest, then 2 hydrogens come up, and then 1 hydrogen. So we've started to shift where we see our peaks. So we know number of peaks, and now we know that they're going to shift based on how many carbons that are bonded to it. Okay, so if this just has 1 carbon bond to it, shifts a little bit, 2 carbons bonded to it, shifts, 3 carbons bonded to it, shifts a little bit. What's a double bond going to do? A double bond is going to help shift those adjacent methylenes higher still. So notice that the hydrogen that's shifted up from a double bond is a little bit higher than just having 3 carbons on it. And then our acetylene hydrogen shifted even higher. Okay, so what we can see from this, and we don't have to memorize these, we're just looking at that they are shifted higher and higher and higher based on how much more electrons are nearby. Notice that we're getting higher because a double bond. We're getting higher because a triple bond, next to a benzene ring, next to an oxygen. Okay, the more electronegative thing, the more electron density you have nearby, the higher and higher the number shifts. Okay, so if you're comparing between 2 things and one has a more electron density to it, think that it's going to be higher than the one without the electron density next to it. So as we go up higher and higher, we have double bonds going in, we have double bonds next to oxygens. Now we're looking at things that are bonded near halogens, okay? The things bonded near halogens range from 3 to 5. And notice that iodine is the lowest, then bromine, then chlorine, then fluorine, okay? The ions are getting smaller and smaller. There's more and more negative charge in a smaller and smaller place. So they shift. This trend right here should follow that electronegativity trend. So you don't have to memorize it, you just have to know the trending of it, okay? Now, the actual hydrogens on double bonds are shifted even higher. The hydrogens on the benzene are shifted even higher. And then as we get to things like carboxylic acids, those go up to the high end. Okay. So the trend you're looking for is how much is it like methane, the CH3 at the end of a chain, and then everything's going to be shifted up from that based on how much electron density is near it, okay? Okay. So that being said, that gets us through N, I, and P. Now we have to do splitting. Splitting, I think, is a little more complicated than equivalent hydrogens, so the number of peaks. However, it follows a really simple rule, okay? And the simple rule is called the n+1 rule, okay? So what that means is n is the number of equivalent hydrogens next to the peak you have, the atom you're looking at. And then the 1 is the actual peak you get from those hydrogens, okay? So when we split, if you have no hydrogens next to the hydrogen you're looking at, it will have a single peak. If you have a set of non-equivalent hydrogen nearby, it's going to split it that number of times, okay? So now that we know this rule, let's apply this rule, okay? So in the case of trichloroethane, we are going to look for the compound. So here's the compound. I'm going to redraw it such that we can draw attention to a couple of things. Cl, Cl, H, C, H, H, and Cl. Okay, so this is exactly the same structure here. Now let's go through our number of peaks, okay? We have 2 hydrogens on a carbon with 1 chlorine on it. We have 1 hydrogen on a carbon with 2 chlorines on it. That means that these hydrogens are different than this hydrogen right here. So when we do our intensity, we're going to see an intensity of 1 here and an intensity of 2 here, okay? But now let's look at the split, okay? So our blue hydrogen here is going to have its own peak because it is its own unique hydrogen. And so it's going to have its own shift, and it's going to have a single peak for that. However, that peak is going to be split n times plus 1 with the number of hydrogens next to it, okay? So there are 2 hydrogens on this, these red hydrogens here. So that means we get 1 peak for the hydrogen here, and then it's going to split 2 more times for a total of 3 because of these 2 hydrogens. So the center, if you can imagine this, the peak for itself is the middle, and then the 2 hydrogens next to it. Even though they're equivalent, there's a total of 2 hydrogens there. So we're going to get a total of 3 peaks. And when we call 3 peaks, we call it a triplet, okay? And a doublet is 2 peaks. Now, why is the red one only 2? Okay, so we get 1 peak for the hydrogens themselves because they are equivalent to each other. So we get 1 peak for those. We have 1 hydrogen next door. That 1 hydrogen is going to split that 1 peak 1 time, n+1, giving us a total of 2 peaks. Okay, does everybody see, actually let me draw it in blue so that we can say the first peak is from the red hydrogens, the second peak is from those hydrogens next to it, okay? Does everybody see where the n+1 rule comes from, okay? The 1 is the hydrogen itself you're talking about. The n is the number of hydrogens adjacent to that hydrogen. Okay, let me define adjacent to. A total of 3 bonds. Okay, let's look at that. There is 1 bond here. I did not mean to erase that. There's 1 bond here between this hydrogen, 1 bond here, and 1 bond here. A total of 3 bonds. Okay, no more. So our n+1 is the peak plus the number of hydrogens that are 3 bonds away. What if it's 4 bonds away? They don't count. They don't split. What if it's 2 bonds away? That means it's on the same carbon. So they probably are equivalent. So 3 bonds is the rule. 3 bonds is the rule. Okay, so the question in the chat is, since the other hydrogen is the same signal, it doesn't count as a third hydrogen. Okay, that's what I'm trying to make very clear here, is that when our end are the hydrogens that are 3 bonds away, if you're 2 bonds away, I'm going to redraw these as red bonds. These 2 hydrogens here and the red bonds here, they're only 2 bonds away from each other, and they're exactly the same. They're equivalent hydrogens, so they don't split each other. Okay, so whenever we have our end, that's the number of hydrogens that are 3 bonds away plus our original signal. All right, let's use that 3 bonds away rule on the next slide here. All right, so we're going to use all 4 rules for this compound here. Okay, notice that these are already highlighted in red, and then these are highlighted in blue, and then the ones in the middle are already black. Okay, so first thing we think about when we think of spin is number of peaks. Okay, so the blue ones are equivalent to each other, the black ones are equivalent to each other, and the red ones are equivalent to each other. So how many, what's our N, our number of peaks? Correct, 3. We got 1, 2, 3. So we have 3 different peaks. Okay, now we have position. Okay, when we think about position, let's look at the one in red here first. Okay, we're going to call this 1, we're going to call this 2, and we're going to call this 3 just arbitrarily. Actually, let me do them in different colors. This is 2, and this will be 3. Okay, so we've done number of peaks, 1, 2, and 3. Let's do intensity now. Intensity is going to be, for number 1, is going to be a total of 3. For number 2, it's going to be 2. And for number 3, it's going to be 2, because there's 2 hydrogens there. So now we've done our number of peaks and our intensity over peaks. Now let's do position, okay? Position, okay. So when we're talking about position, we're talking about how far it's shifting away from being that perfect little CH3 group attached to a silicon, okay? And we know that the closest of these 3 that's closest to that CH3 group by itself sitting next to a silicon has to be the one at the end here, because it's a CH3, okay? So we think it's going to be closest to 0. So this is going to be peak number 1 right here. Now, the one next to it is a one with 2 CH, it's a CH2, but it's bonded to a CH3 and it's bonded to a CH2. So that's almost a methyl group, but not quite. So it's going to be shifted up from there. So that means our peak 2 is going to be shifted up from there. Okay, and just to be sure, let's look at those last 2 hydrogens. Those last 2 hydrogens are bonded to a carbon that's bonded to a chlorine. That chlorine has the most electron density of any of those systems, therefore it's going to be shifted furthest up. It's furthest away from being an isolated methyl group, making it going to be our peak number 3. Okay, so we have number of peaks, we have intensity, we have position. Now let's do our splitting. Okay. All right, so let's write our rule up here, N plus 1. Okay, so let's start with peak number 1 with our rule here. So we have 3 hydrogens here, but those 3 hydrogens are equivalent, so that's our 1, okay? So within 3 bonds of any of those hydrogens, right, we have 1, 2, and 1, 2. So we have a total of 2 hydrogens that are non-equivalent that are 3 bonds away. Notice these hydrogens over here don't count because those are 5 bonds away. So those aren't going to split, okay? So we have to go back and just say, oh, look, those are the only 2 that are 3 bonds away. So our N is equal to 2. So N is equal to 2 here. So we have 2 plus 1 equals 3 peaks. So that means our position 1 should have 3 peaks, okay? Let's look at our position number 3 now. Okay, that's our blue one right here. So we have 2 hydrogens that are equivalent, so that's our 1 plus N. And so if we look at the connection here, we have 1, we have 2. We only have 2 hydrogens within 3 bonds. Therefore, we have 2, which means we're going to have a total of 3 peaks. So our peak 3 should be split 3 times. Total of 3 peaks, sorry, split by those 2 hydrogens for a total of 3 peaks. All right, now let's look at number 2. Position 2 here. Okay, so in position 2, we get 1 peak for the hydrogens themselves, okay, plus N, okay? So let's see, we have 1 hydrogen, 2 hydrogens, 3 hydrogens going the one direction, and the one on top's the same, so we don't count that one. And we have, let's see, that's 4 hydrogens and 5 hydrogens. So that means we have 5 hydrogens that are non-equivalent hydrogens plus 1 is equal to 6. Okay, which means we should have 6 peaks in this right here. Okay, so let's blow that up and see if it's true. So if we blow up our NMR, and this is actually how we do it on the computer too, we see that we have our first peak has 3 peaks, 1, 2, and 3. 1, 2, 3. We see our second one has 1, 2, 3, 4, 5, 6. And we see our last one has 1, 2, 3. Okay, so we've applied all 4 of our rules. Okay, let's back it out. Our N, number of peaks. We have 3 different types of hydrogen. We have 3 different peaks. We have our intensity. Notice the numbers here are the number of hydrogens on each of those. There's 3 hydrogens here, there's 2 hydrogens here, there's and then there's 2 hydrogens here at the end. Okay. Let's look at P, position. Most like the methyl group was number 1, right here. The next most like the methyl group was at position 2, and our least like the methyl group of this set was number 3. So they're shifting further and further away from 0. And then our spin coupling, our spin-spin peak splitting based on the number of hydrogens that are 3 bonds away from the hydrogen that's being split, number of hydrogens plus the hydrogens themselves, N plus 1. Okay, so we've used all 4 rules and we've identified each and every peak in our spectrum. All right, questions on that? Okay. Oops, sorry, one more. There we go. Okay. So, all right, let me do one thing right here. And actually, let's take a break. Let's take a break, and we're going to predict, just by looking at structures, what we think the structure should be. And we're going to use all 4 of these rules again. Okay. So here's what I'm going to do. I am going to stop recording and come back in 5 minutes, and we'll do predictions.